Okay, on this problem, what we're going to be doing is we're going to find the points of inflection and we're going to discuss the concavity of the function again. This time we're going to find the points of inflection as well. I think this one is much easier to take the derivative rather than doing product rule. Just spending a little time multiplying out this x minus 4 times x minus 4 times x minus 4. Because I have to find those possible points of inflection, I may just want to spend time doing this, which is what I'm going to do. I'm going to multiply those two together first, which gives me x squared minus 8x plus 16. Then I'm going to take it and I'm going to multiply those two together. So I'll end up getting x cubed minus 8x squared minus 4x squared plus 16x plus 32x minus 64. Now I didn't go in order on those. I went in order that so I would have them next to each other so I could add like terms. So my function then would be x to the fourth in my add like terms while I distribute this negative through. So I get negative 12 x cubed plus 48 x to the second minus 64x. So the first derivative ends up being 4x cubed minus 36x squared plus 96x minus 64. My second derivative is 12x squared minus 72x plus 96. Now, this one I want to find out where it's equal to 0. If there is no values where it doesn't exist, I am going to be able to factor out a 12, so it makes it easier to factor. So I get x squared minus 6x plus 8. And then I'll go ahead and start factoring this further. It'd be x minus 4x minus 2. So there's two possible points of inflection. Those are at 2 and 4. I am testing the second derivative. Now, we're also supposed to find the points of inflection. So if the concavity changes, then we'll say that the points of inflection were at 2 comma something and 4 comma something. So these are the possible points of inflection right now. I'm going to test the second derivative, so I'm going to plug 0 in for my second derivative right here. Or right here, doesn't matter which one. When you plug in 0, you get 0 minus 0 plus 8, so you get a positive value. When you plug in 1, try 1, we have 1 minus 6, that would be a negative 5 plus 8 would give me a negative value. And then on this next part here, I'd have 5. 25 minus 30 is negative 5 plus 8 is a positive value. And I said I was trying 1 here. I meant I was trying 3. And 3 does give you a negative value. So I end up having concavity changing over here at 2. And where do I get my y value? Way back up here at the beginning. So if I plug 2 back in up here, my y equals 2 times 2 minus 4 cubed. 2 minus 4 cubed, that would be negative 2 times negative 2 times negative 2, which is negative 8, times 2, which is negative 16. Plug 4 in up here, and you end up getting 0. So the points of inflections are 2, negative 16, and 4 and 0. Your concavity is going from 0 to 2 and 4 to infinity. Those are the concave up intervals. And then the concave down interval is from 2 to 4. So that one is concave down. Okay, this is a problem from your assignment. I'm just going to change this to a 3. This is number 27. So feel free to go ahead and put this with your assignment. The first thing I'm going to notice is that it does say find the points of inflection and discuss the concavity. So I am talking about the second derivative. And this is going to take a while to do because the second derivative is going to be much more difficult to find. So my first thing I'm going to do is go ahead and write this function with a half exponent. I'm also going to take note right here that the domain of this function is going to be from negative 3 to infinity. Negative 4 gives me a negative number underneath my square root, so the only parts of this graph that even exist are from negative 3 to 0. And this could be at negative 3, because negative 3 will work. So I should have used a bracket. Let's go ahead and find the first derivative. The first derivative would be first times the derivative of the second plus the second times the derivative of the first all over. That's it. I was thinking quotient rule for a minute. What this gives me, I am going to need to combine these terms because otherwise it's going to make the second derivative very difficult. So one of the things I said that you needed to be able to do was combine like terms. This does go on the bottom of the fraction, so does the 2, and this x stays on the top of the fraction. And this one just has a square root of x plus 3. So I need to combine these, which means I need common denominators. My common denominator is going to be 2 square root of x plus 3. 2 square root of x plus 3. This one doesn't change, however, this one was over 1. So when I multiplied the top by 2 square root of x plus 3, I ended up getting 2 times x plus 3. So my first derivative will be rewritten as, this is x plus 2x, so 3x, and then I have plus 6, so I'm distributing those through, all over 2 square root of x plus 3. Now, I said this was much more difficult. The second derivative now requires me to do a quotient rule. So we are going to go ahead and find this derivative using the quotient rule. Now we do want to think of this as 2x plus 3 to the 1/2 power, so I'll write that off this side. Bottom times the derivative of the top minus the top times the derivative of the bottom. The derivative of the bottom would be 1/2 times 2 would give me a 1, so just x plus 3 to the negative 1/2 all over bottom squared. Well, 2 squared is 4, and the square root of the x plus 3 squared is just x plus 3. So I'm going to come up here to finish the simplifying. The second derivative would then be 6 square root of x plus 3 minus, I'd have the 3x plus 6 on the top and the square root of x plus 3 on the bottom, and then a large fraction with the 4x plus 3 on the bottom. Well, I now need to combine like terms up here. So what that's going to give me is I'm going to want to make the common denominator be square root of x plus 3 on the bottom. So that's going to give me 6 times x plus 3 on the top, and then I'd keep my 3x plus 6. Now this is being subtracted here, so I've got to make sure I distribute my negative through. My second derivative then would be 6x minus 3x, so let's just change that to be a 3x. Then I'd have 18 minus 6. 18 minus 6 is 12. And all over the square root of x plus 3. Oh, and I lost my huge denominator. I'm going to have to finish this on the next video. Continuing on with this problem, which I said was a much more difficult problem, we want to figure out where this second derivative is equal to 0, because our ultimate goal is to find those points of inflection and where our concavity changes. So when I put 0 in, I'm going to take note that I've got places where it does not exist here at negative 3. So it does not exist, the derivative does not exist, because up here, remember, it was an endpoint. So of course it does not exist there. But I'm really just concerned where it's going to equal 0. So that would be on the top of this fraction right here only. So I'm going to just take that part and set it equal to 0. And I'll find out that the x value that will give me a 0 would be negative 4. Well, negative 4 is not even in my domain, so there are no points of inflection. So this graph simply is concave up or concave down. Remember, it only goes from negative 3 to infinity, so I can only test this one interval. So what we're going to do is we're going to look at the second derivative, and we're going to try one of those numbers. I'm going to pick 0 because 0 is the easiest thing to work with. When I plug in 0 in for my second derivative, what kind of concavity do we have, positive or negative? Well, this would give me positive over a positive over divided by a positive. I don't even care what the value is, I just know it's positive. So it's going to be concave up from negative 3 to infinity. And that's the end of that problem. Remember, that is part of your assignment, so you can make sure and write that into your assignment.